Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, my name is Wojciech Samek. I'm heading the AI department here in Berlin at Fraunhofer Heinrich Hertz Institute, mainly focusing on developing explainability methods. And I'm very happy to introduce our speaker today, Graham Taylor. Graham is a Canada Research Chair and Professor of Engineering at the University of Guelph. He co-directs the University of Guelph Center for Advancing Responsible and Ethical AI and is the interim research director of the Vector Institute for AI. He is a recipient of multiple Best Paper Awards. He co-founded a company and has been named as one of Canada's top 40 under 40. So he's a very active person, and I'm happy to have you, Graham, and I look forward to your talk.
Thanks, Wojciech. It's really a pleasure to be here. It's a fantastic opportunity to reach an international community. So I look forward to sharing research with you. So I'm going to share my screen, if that's okay now.
Yes.
Great. Okay, so Wojciech, let me know if there's any problems seeing my slides, but they should be up now.
They are up. Everything's fine.
Okay, wonderful. So thanks very much. I'm going to talk today about a particular research project that's going on in my group right now. And this is the idea of being able to predict the parameters of a neural network without training it. So in the last 10 years, deep learning has dominated artificial intelligence. And this is apparent by its adoption in the high-tech industry and the level of hype in the mainstream media. So what is deep learning? Well, it's the modern practice of neural networks. And some would say it's modular differentiable computing. It's been built on the backbone of learning by stochastic gradient descent. And what's fascinated me for a very long time about deep learning is that a lot of deep learning is based on 1980s and 1990s technology. For example, backpropagation, an algorithm that's used as core to learning by stochastic gradient descent. Also, the architectures that are very popular, like convolutional neural networks, also late 80s, early 90s technology. So the 2014 view of why deep learning suddenly started working in the aftermath of the now very famous 2012 Imagenet competition is that as time went by, we were able to acquire more data and more computing power, and this allowed the capacity of machine learning models to grow accordingly. So as you can see here in this plot, we pushed out on data towards data sets with millions, and now in cases of hundreds of millions or billions of examples. We had the introduction of general purpose GPU computing enabled by NVIDIA's CUDA library. This completely changed the scene, and it essentially enabled cheap personal supercomputers that were highly optimized for the kinds of computations performed by deep learning systems. So you can see on the axis coming towards you, pushing out with a teraflop, even now upwards of 10 or more teraflops available at a desktop. Many more, of course, available in compute server platforms. And so what the data and the compute have enabled are much more complex architectures. And so this is now being pushed up on the vertical axis. And it's not that these architectures couldn't be envisioned in the 80s and 90s. we were just never able to train them on so much data and in so little time. So the idea is that deep feed-forward neural networks and convolutional neural networks and those sorts of architectures were in many ways premature. So we didn't have enough data and flops to train them, and they would overfit and be too slow to train. Many thought they were the problem was local minima. This view has changed to some degree. So now I would say the more modern kind of 2019 view is that local minima were never really the issue. And in fact, something magical happens when you push models into a very high capacity or complex regime. So what I'm showing is some research from a paper by OpenAI in 2019. And the purple curve shows how test error, and that's a proxy for the thing that we really care about in deep learning, which is generalization error, basically the ability to perform on examples you've never seen before. We see how this test error change as we increase the model size. So going along the x-axis from the left to the right, we have the model size in terms of the width of a ResNet 18 network being expanded. And the performance, as you see, it improves because the error is dropping, but then it gets worse. So it starts to increase a bit, and then it starts to drop again. And so neither the classical statistical perspective that too large models are worse, so that's in green, or the modern machine learning paradigm that bigger models are better, that's in orange, really hold up here. So something that's happening is, like I said, it's kind of magical, and it's not explained by our intuition from classical machine learning or modern machine learning. Now, in this plot, we see what's being called the double descent phenomenon, where it's actually leading to a regime, an intermediate regime, where bigger models are actually worse until we push their capacity very far out. And the peak in error occurs around what's called the interpolation threshold. So the point at which models are just barely big enough to perfectly fit or memorize the training set. And the mechanisms behind this phenomenon, this sort of critical regime of learning and this double descent phenomena, it's still an open research question, but we are convinced that something very special is happening when we use big complex models. And so there's a romanticized notion of deep learning being the end of feature engineering in machine learning. I'm sure many of you have heard this many times. There's no doubt that feature learning has reduced the need to do a lot of feature design by hand. However, in step with performance, and what I have just been showing is that models have grown in complexity. So from inception to VGG to ResNets to more modern vision transformers, architecture engineering has become the new feature engineering. And this blog post by Stephen Merity came out in 2016. I remember seeing this and just thinking, yes, this is absolutely right. We've gone from a regime of feature engineering over to a regime of architecture engineering. What does this mean? It means we've been very focused on increasing performance, typically measured in accuracy, and to achieve better performance, we've been working very hard as deep learning practitioners to create new architectures with fancy names. So the AlexNet of 2012, the ResNets of 2016, the VGDs of sort of 2017, and we continue to push out. This plot is from Eugenio Curlicelio's blog. I think it's the second version of this, and this is current as about 2019, where we're actually starting to see some architectures that have reduced parameters and are still relatively performant. But the best architectures, you can see by the size of the circle here representing the number of parameters, the best architectures are indeed high capacity models. What's also interesting here around the time 2019 is that we saw a rapid increase in terms of increasing architectural complexity and model capacity and a great gain in performance, but there was eventually somewhat of a saturation point. And so the question here is, have we reached kind of the limit of human ingenuity doing architecture design, increasing the complexity of models, and do we need something more? So here the auto machine learning community comes to the rescue. So I attended a talk by Frank Hutter from the University of Freiburg in the fall, and he virtually visited the Toronto Machine Learning Summit, and he did this very nice framing of deep learning 1.0 and deep learning 2.0. So Frank's view of deep learning 1.0 is very much this manual architecture engineering that's targeted purely towards one metric, which is performance. We saw this in the previous plot. And there's a human bottleneck in this pipeline. There's a deep learning expert who designs the architecture and carefully chooses the hyperparameters. And of course, compared to traditional machine learning systems, deep learning systems are trained end to end. So this is the advantage they deliver. They do feature learning and they do the task, for example, classification together, and they're designed to maximize performance, but it's a costly process of trial and error, which ignores other considerations. So for example, the fairness of a model or the robustness to out of distribution examples or adversarial examples. Deep learning models are known to have poor calibration. They're often overconfident in incorrect predictions. We've just heard already that there's a movement in explainable AI and trying to make these models more interpretable and user-centric. There could also be latency and memory capacity issues in terms of deploying them in real-world devices. So there's a lot of different criteria that deep learning 1.0 tends to ignore, and there's a huge reliance on deep learning experts. So in Frank Hutter's view of deep learning 2.0, this is automation of the deep learning pipeline. So the deep learning expert is now replaced by an auto machine learning system that employs meta learning and optimization over the architectures and hyperparameters. This requires much less machine learning know-how to use, and it provides very clean interfaces to domain experts who can specify objectives like fairness and robustness and calibration and interpretability and latency and so forth, and other criteria that are important to those domains. Now, Frank's argument is that deep learning 2.0, the use of auto machine learning, boosts productivity for domain experts and deep learning experts as well. Its main requirement is compute, and we've seen that compute improves over time. This is what the deep learning revolution has effectively been built on, including GPUs. The only issue, or I would say the primary issue of this view, is that at the heart of most auto ML systems is an expensive iterative algorithm known as stochastic gradient descent. And so a search over architectures by an auto ML system means training potentially millions of architectures to convergence and evaluating their performance. And so this requires an enormous amount of compute, irrespective of whether the ability of compute is improving. So this brings us to the story of our project I worked on with my PhD student, Boris Kniazev, who is at the University of Guelph in Vector. And the idea was catalyzed while Boris took an internship at Facebook AI Research, which is now Meta AI. And he was co-advised there by Adriana Romero and Michal Drodzel. And I want to give them a lot of credit here. They were fantastic internship advisors and mentors to Boris. We worked together on this project, and everybody on this slide has contributed in different ways, and it's really a group effort. And so Boris was suddenly exposed not to academic style resources, but Facebook style resources. And he had this idea, or really a question, of whether we still needed iterative optimizers. Could there be something other than SGD or other flavors of iterative optimization that could be used in place for tasks like neural architecture search or other aspects of auto ML. So we set out to propose an alternative. And what we did is we created an alternative to SGD called a graph hypernetwork that accepts as input a computational graph describing an architecture, and it can output its parameters in a single forward pass. So this sounds a bit crazy, but it actually works. And so what we're seeing in Boris's tweets below, for an architecture it's never seen before, like a ResNet 50, it can output all 25 million parameters and achieve close to 60% on CFAR10 with no trading. So for those of you who are familiar with CFAR10, that data set, it's by no means a state-of-the-art result. Networks can easily attain 90% plus accuracy on CFAR, but the fact that you can do this in less than a second, even on a CPU, is quite astounding. And also a modestly performing neural net, like a 60 or 70% CFAR10 net, has many uses, indeed, in applications like neural architecture search. Okay, so from a human-centric AI standpoint, why do we care about this? Well, as AI and machine learning have become more prominent, there is a concern about the rising costs of computation. And most of this computation is associated with iterative optimization of deep nets. So I previously argued that feature learning has supplanted feature engineering, but enormous human and computational effort is devoted to engineering new architectures. So Frank Hutter, who I mentioned, and others have promoted AutoML as a way forward, automating architecture engineering with tools like neural architecture search and reducing reliance on deep learning specialists, which are key bottleneck for lesser resourced institutions like governments and universities. Yet AutoML, and specifically neural architecture search, they're often singled out as using extraordinary amounts of compute. So there's this very well-known paper now by University of Massachusetts Amherst authors from 2019. And this argues that in particular, natural language processing models are huge overusers of compute. Now, the scale of this problem is still being debated. So in a paper published late last month, Google authors were very critical about some of this work that highlighted neural architecture search as a source of emissions. Now, some papers subsequent to this University of Massachusetts Amherst paper had confused the cost of running NAS as the training cost of the model that was discovered. So the cost of doing a neural architecture search, which trains thousands or maybe more models, is obviously several orders of magnitude higher than training a single model. And so the key argument in this recent Google paper is that the carbon footprint of ML could indeed be shrinking, not increasing, as the result of what they call the 4 M's. And so in this plot on the right, we're seeing in succession these 4 M's being applied to a model. So let's start with basically a 2017 style vanilla transformer model being trained on a P100, which is effectively like a GPU that's available at the time. And we have a certain amount of compute. If we train an efficient variant of a transformer, that can reduce the carbon emission by 4 times. And so that's what we're seeing in the first, sort of the leftmost dot here. We get a 4 times reduction by the first M, which is model, train an efficient model. And also on that plot I showed you before from Eugenio Culicherio, when we saw mobile nets and squeeze nets and so forth, this is an example of training for a particular task, a more efficient architecture. Now, if we move to the next M, which is the machine, instead of training on a P100, let's train on something like a TPU, a tensor processing unit that is very specialized to deep learning. And this is a modern TPU, a TPU v4. And so using this newer generation ML hardware, we can get an additional 14 times improvement. So now we're up to 57 times the carbon reduction. If we use efficient cloud data centers, these will yield an additional 1.4 times over an average data center. So this is the third M, which is mechanization. So now we're up to an 83 times improvement. And finally, the fourth M is map optimization. This means choose a location that has access to a low carbon energy source, and this will reduce the footprint by another 10 times. So now we're up to a 747 times reduction compared to the transformer that was trained in 2017. Now, irrespective of where you sit on the debate about the carbon footprint of ML models, the current approach to training networks using SGD variants for hyperparameter optimization or architecture search is extremely wasteful. So every time you run SGD and initialize a network to have random parameters and start training it, the optimizers we currently use completely disregard past experience that could be gained by optimizing thousands or millions of nets. So a deep learning practitioner will gain experience, and that will be in their head, and they will think about certain choices that are made. But you would imagine that this experience of training many nets, an auto ML system, of course, would have experience training many more nets than a human would ever have training. And so we would like this experience to effectively stay in the system. So the question we set out to answer is, can past experience be the key to reduce reliance on iterative optimization and its high computational demands? And so I want to note that using parameter prediction in place of SGD is orthogonal to Google's 4Ms. So it can complement all these additional proposed strategies. So here is in this picture is basically the two alternatives. We can do thousands or millions of iterations of SGD, or we can have a graph hypernetwork that accepts an architectural description of a novel unseen architecture and predicts its parameters in a single forward pass. And so I showed you before that we can achieve something like 60% accuracy on CFAR10 on a famous architecture, a ResNet 50, that we have never observed before. If we allow ourselves to measure performance on many different architectures, we can actually gain up to 77% top one accuracy on CFAR10 and up to 50% top one accuracy on, or top five accuracy on Imagenet. Okay, so let me dive in now a little bit more technical detail on how this works. So batches of architectures that are represented as computational graphs are fed to our variant of a graph hypernetwork. And the graph hypernetwork outputs parameters for these different architectures. And those parameters are used in nets that process batches of images, which we see coming in on the right-hand side. So the loss is computed using the architectures with predicted parameters, and it is back propagated all the way back through this graph hypernetwork, or GHN, to improve parameter prediction. So we build on the graph hypernetwork that was proposed in 2019 by colleagues at University of Toronto. And these original GHNs that we call GHN1, they're not really designed for drastically different unseen architectures. And so we needed to make several improvements to make them work in a setting where we might show architectures that are wider or deeper or contain different changes. For example, not using batch normalization or having denser connections. We want this model to be fairly robust to those sorts of changes. So we had to improve on the original GHNs by proposing several enhancements: metabatching, virtual edges, and parameter normalization. And I'll talk about those slightly later. So this whole pipeline at a very high level looks a lot like meta optimizers, but in the case of doing meta optimization, those types of models use recurrent neural nets that predict gradients, mimicking the behavior of iterative optimizers. So the behavior of those meta optimization techniques that have been proposed in the literature is more about learning to optimize rather than learning to predict parameters. So meta optimizers still need to be tuned for a given architecture and need to be run expensively on the GPU for many iterations. Again, we're not proposing updates to gradients. We're actually proposing a set of parameters that will be performance like trained parameters that's coming out of a multi-step iterative optimizer. So to collect a data set of architectures that are diverse and can train such a graph hypernetwork, we identified 15 of the most common operations in neural networks for vision tasks, such as convolution, batch normalization, summation, pooling, multi-head self-attention that's used in the vision transformer, and so forth. And we can use these operations to describe diverse deep neural nets. So for example, we can use these individual blocks to represent a well-known ResNet 50 or a vision transformer, and you can see the types of operations that are used in these different architectures are different, and the way that they're connected to one another are also different. So taking just a closer look at how we represent networks to our graph hypernetwork, we have at each node, so the nodes here are colored, the node is represented by an encoding of what it is. So for example, we see node 1 is an input node that's represented in red. And we also encode the number of parameters and their size. So there's no parameters associated with the input node, but when we go to node 2, we note that this is a convolution node, and we have parameter dimensions of 64 by 3 by 7 by 7. And then we move the node 3, and we have some input features which characterize the fact that it is a bias node, and it's a 64 by 1 by 1 by 1 tensor. Node 4 is a pooling load. Again, no parameters here. Node 5 is another bias node, and so on and so forth. And then when we get to the end of the network, we have node 160 being a global average pooling operation with a certain parameter tensor. And then we have the final node being another bias. And basically, this is our ResNet 50, 161 nodes. The input features X being these encoding of the type of node and the parameter tensor, and then also the adjacency matrix, which is encoding the connectivity of the nodes. So in other words, the forward pass flow. So we call this data set of diverse architectures deep nets 1 million, and we generate them by uniformly sampling depth, width, and an operation for each node. And so key to this deep nets 1 million data set is we're not storing any trained parameters. We're just storing the architectures. So again, this is like meta learning. We're not trying to train the graph hypernetwork to map trained parameters. We're training it to predict parameters sort of on the fly and be used in making predictions on, say, classification for CIFAR10 or Imagenet, and backpropagate that task performance through the GHN. So we train the meta model on these 1 million induced distribution computational graphs. So these are the type that we see on the left-hand side here. We've got also a validation set of 500 and a test set of 500, which we call, again, in distribution. This validation and test set are very much like the type of architectures that match these 1 million training architectures. But the key focus of this work is on out-of-distribution generalization. So we use several types of distributional shifts. So as you see here, we evaluate on wider architectures or deeper architectures or dense architectures. We have batch norm-free architectures, and then we have specific architectures like a ResNet 50 or a vision transformer, which are unlike any of the architectures that are in the in-distribution 1 million computational graphs. And so another interesting thing we see at the bottom here are some statistics on these networks. So we can see moving, comparing the training distribution in these violin plots at the bottom. For example, the violin plot at the top is the number of nodes. And so we see that, for example, in the deep and dense classes of out of distribution architectures, they have a much wider characterization of networks with number of nodes. They can go right up to, say, 1200. And then if we look on the bottom violin plot, this is the distribution over number of trainable parameters. So we see that some of these architectures, like the wide architectures or the deep or dense or batch norm free architectures, they have considerably different, like several orders of magnitude more trainable parameters than the 1 million architectures that are in the training set. Okay, so I'm going to get a little bit more specific about how we actually train these networks. So this is the plot from before, but effectively, the reason this works is that the parameters of the graph hypernetwork are improved based on a gradient step update using the current architecture whose parameters are being predicted. So we're likely to predict better parameters for the next architecture since training architectures are drawn from the same distribution. And so the GHN's ability to predict good parameters, it gradually improves after each training iteration. So I have here at the bottom the loss function. So I'll just go through kind of term by term what's going on here. So let me just talk about the sums first. So the outer sum is a loop over batches of images. And so that's common to training deep neural nets. We sample batches of images, say from CIFAR10 or Imagenet. The inner loop is a loop over metabatches. And I'll give more specifics about that in a moment. But for each batch of images, we actually sample multiple architectures. And so an architecture here is A, an image here is X. And so HD is our graph hypernetwork, which accepts an architectural description, this computational graph, and using the GHN parameters theta, produces the parameters for this architecture A. Okay, so we're going to use this net parameterized by the output of the graph hypernetwork to make a prediction. So a prediction f of x on this batch of images predicts some labels. These are compared to ground truth labels. We compute standard multi-class cross entropy loss, and that gives us a loss over this batch of images using different architectures. And those are summed, and then we just do backprop again with we're going to update the parameters with respect to theta, which are the parameters of the graph hypernetwork. So again, much like meta learning. So I'll go through some key improvements over the first version of graph hypernetworks. One problem is that computational graphs, as the sort you've seen me display, often take the form of very long chains with a very few incoming or outgoing edges per node. So this particular structure can hinder long-range propagation of information between the nodes. And so the literature has explored this issue in different ways, including stacking GHNs. But what we do is we add virtual long-range connections to the graph, which we're displaying here in green. So these virtual connections are weighted based on the shortest path between any two nodes, U and V. And so their intensity is being shown here, sort of the darker green, the shorter the path between the node, and more strength then goes on those virtual edges. And so to avoid interference between the real edges in the computational graph and these virtual edges, which are used to assist in gradient flow, we introduce a separate MLP to transform the features of the nodes that are connected through these virtual edges. And we redefine the core message passing operation in the graph hypernetwork. So it effectively has two parts to it, real edges and virtual edges. The second enhancement we make is to deal with the problem that iterative optimizers use variance stabilizing initializations, but hypernetworks, which predict parameters directly, are subject to exploding or vanishing activation. So this has been observed before in the hypernetworks literature, hypernetworks being networks that predict the parameters of neural networks. And the way that we address this in our approach is to apply operation-dependent normalization. So convolution and fully connected layers use a fan-in scheme that's inspired from things like He and Glorot initialization. The parameters of normalization layers such as batch norm and layer norm, as well as the biases typically normalized as constants, are normalized using the squashing function that has a temperature parameter. And so what we see here in the plots on the right are, we'll just look at the top one for a moment, which is sort of the linear scaling. A GHN1 in orange, as we progress through the layers of the network from left to right, have very strong variance on the activations. We can get a little bit more insight by taking a log scale on the y-axis, and we see the plot at the bottom. Whereas if we apply these normalizations, we actually see stabilizing of the activations. Our GHN2 is in red, and SGD trained nets are in blue. So the idea here is to use these operation-dependent normalizations to imitate the distribution of models that are trained by SGD, because the processes here are very different. Like SGD is this, you initialize the rates randomly and you do these small updates iteratively, whereas graph hypernetworks are predicting parameters in one shot. So there's this idea of instability in parameters that are predicted in one shot, and the inability to use existing activation variance control strategies. And this seems to work, as you can see. On the bottom, the red has considerably reduced variance in activations throughout the network. Okay, and the final improvement that we make over GHN1, I know this is kind of in the weeds, and I will back up to sort of more high level description, but this is for the technical people who want to know sort of how it really works inside. We introduced this concept of metabatching, which I mentioned before. So the original GHN1 updated its parameters based on just a single architecture that was sampled for each batch of images. But it can be useful, that we've seen sort of in vanilla SGD training, to use larger batches of images. And so when we use larger batches, we can often speed up convergence by reducing gradient noise and improve the model's performance that way. So we just do this meta batching where for a batch of images, we use multiple architectures. We therefore get larger effective batches. And we have this meta batch size parameter BM as a number of architectures that are sampled per batch of images. And this is quite simple to apply. We're just using an averaging operation to compute the gradients of the loss with respect to the GHN parameters theta. And we can see on the right, in terms of the training loss, up on top, using a batch size of 8 is able to significantly reduce the loss and to reduce its variance over the course of training. Effectively, you can do, because you have these larger batches, you can do less total epochs. So on the bottom, we're kind of normalizing the training progress. So we have a smaller number of epochs, 300 for the metabatched model, and then we have the equivalent for the non-metabatched model, which is 2,400 epochs, and we're plotting them both on a common scale, which shows training progress. And again, this is not about sort of getting more updates. It's really about the benefits of using large batches, which have been observed before. Okay, so for now, let's go to the results. How does this actually work? So we'll first look at CFAR10. So the average accuracy of networks with predicted parameters on test images of CFAR10, we can see using a GHN for the in-distribution architectures is around 51.4, and using these additional improvements to graph hypernetworks to, as we just saw, parameter normalization and virtual edges, metabatching, and so forth, will instantly, even within distribution, give a performance enhancement up to 66.9. And we saw one architecture get 77.1% accuracy on CFAR10. Now, when we go to out of distribution architectures, the ones I mentioned before, much wider, deeper, or denser than seen at training time, there is a really large improvement. And so most of the work that we did was with respect to improving out of distribution performance. So GHN1, the original GHN, really doesn't perform well at all. It will get 19.2, which is better than chance, and 18.2% test accuracy, but we're seeing 58.6% accuracy on a ResNet 50. It's interesting that we don't perform as well on a vision transformer, and this is something that still we're investigating. We also have on the bottom an Oracle model. This is a model that has been trained for 50 epochs of SGD, which is considerably longer than the sort of less than a second prediction in a hyper network. And sort of the performance there we're seeing when we're restricting to this Dart search space are like 88.5% on average and a maximum of 93.1. So we see overall that the GHN2 generalizes well to unseen architectures, even out of distribution ones like ResNet 50. And we're seeing improvements by the GHN2 over the baseline of GHN1, more than 20% gains. On Imagenet, which is a larger data set in terms of both its size and number of examples, we still see that GHN2 generalizes well to unseen architectures, even if they're OOD. So random chance on Imagenet is about 0.5%. There's 1,000 classes in that data set. And we're seeing in distribution performance of 27.2, top 5 average accuracy, with some networks that give 48.3% performance on a 1,000-way classification. In terms of out of distribution performance, we see networks that are on average predicting 19.4% top 5 accuracy, and networks that are capable of predicting 47.3% top 5 accuracy performance. And I want to point out here, when we look at the GPU seconds or the CPU seconds column, we're talking a 4 or 5 order of magnitude improvement in terms of the time to arrive at performant parameters on a GPU or CPU respectively. So the sort of the matching network in terms of performance would be something like a SGD model for 5,000 steps. Again, we're 10,000 or 100,000 times faster for similar performance. And then again, it's sort of our Oracle model at the bottom, achieving something like 81.8%. So that would be our future goal, is to get to something like that. Now, another side benefit of our GHN approach is that we can use it as a general purpose initializer for arbitrary neural networks. So for example, if we take a GHN2 model that's been trained on ImageNet classification, we can retarget it for different tasks. So here we show one task being few-shot image classification, another task being few-shot object detection. Those are the rightmost 2 columns. And we compare our results here to pre-training the same network on ImageNet, which is much more costly. So parameter prediction on the 100-shot CFAR10, which is a few-shot task, performs similarly to an ImageNet pre-trained network with 2,500 pre-training steps. And on the Penn-Fudan object detection, which is the few-shot object detection benchmark, we're performing similarly to this ImageNet 2,500K or 2,500 pre-training step model. And so again, looking at the GPU seconds, it takes us 0.7 seconds to initialize and pre-train our model. For this 2,500 pre-training step ImageNet, it's 1,500 GPU seconds to perform. And so there's several beneficial side effects of GHN2 beyond predicting parameters and using them directly in tasks. So it can learn a very strong representation of neural architecture. So remember, this GHN that is being trained on a task is being fed inputs of computational graphs. So embedded in this graph neural network are representations of neural network architectures. And so what we can do is we can compute an average representation across nodes, and this will give us a graph embedding. So for example, a 32-dimensional vector, which represents the properties of a computational graph representing an architecture like ResNet 50 or Vision Transformer. And so using our GHN, we're able to rank architectures by different properties. And so we can efficiently and effectively search accurate networks or robust networks or networks that are fast to process images or networks that are fast to converge. And this will also allow us to do a neural architecture search without training networks to convergence. So we can just do a forward pass in the GHN, get this representation, predict the properties, and use that as the inner loop of NAS compared to using SGD as the inner loop of NAS. We tried NAS by directly predicting and evaluating parameters, but it didn't work as well as using this separate network trained directly on the embeddings of the GHN. So just to show you how this does, the architecture chosen by GHN2 is the best in terms of clean accuracy. Will achieve 97.26 on CFAR10 when trained with SGD according to the standard NAS protocol. So this result is competitive with standard NAS approaches, but it is only a fraction of the time it takes to do a normal NAS. And we also compare on all these properties. So for the NAS, we're using clean image accuracy, but I mentioned we could do noisy image accuracy. So this is like Gaussian white noise at test time. We can predict the inference speed or the convergence speed, and we compare this to a model called Neural Predictor, which is designed specifically for this task. And we perform very favorably compared to that. Okay, so winding down, I'll just briefly go over some limitations that we saw in our model. I showed you how parameter prediction worked in 2 low data tasks, but it failed in the case of more data. So doing fine tuning on a network whose parameters are predicted, there's something that's happening to it that puts it in a regime of the parameters that kind of stunts its future opportunity in the large data setting. So the analogy that I've been using is like, imagine someone came to you and said you could take a baby and put them through this special curriculum, and they would suddenly have the knowledge of a toddler, even though they were only a few weeks old. But then if you took that toddler and sent them to sort of a standard school curriculum, when they grew up and you saw how they were performing when they were, say, 30, something would be very wrong. Like there would be something about doing this process early on that just sort of set them up for failure. And that's sort of the same thing that we're observing in these nets. So it works in the specialized few shot regime, but we really need to understand what's happening here when you use parameter prediction instead of SGD pre-training. The other thing that's a limitation, of course, is that we train these graph hypernetworks specifically to a task and a data set. So we have a CFAR10 classification GHN, and we have a Imagenet classification GHN. But one advantage of iterative optimizers is adapting very quickly to new data sets and loss functions. So we'd like to be able to change the objective. There's no reason why we couldn't do self-supervised learning. And there shouldn't be a reason why we can't have GHNs that are performant across different data sets. So in conclusion, let me just say that we've been able to show that leveraging the experience of training many networks is a feasible way to approach the compute challenges associated with deep learning. We've also derive this interesting test bed for graph neural network research, because GHNs are a type of graph neural network, and improvements in graph neural networks should improve GHNs for predicting parameters. We achieved surprisingly good results in our task, being able to predict performant parameters in less than 1 second, even on a CPU. And this certainly reduces expert knowledge. This Colab notebook that I'm showing on the right, I encourage you to check it out. Input your own favorite architectures and generate candidates for parameters with less than a second. So the downstream gains I talked about were efficient estimation of network properties like inference time or performance. We're able to initialize neural nets. We could also do interesting things like network compression. So there's many sort of architectural design activities that should be made more efficient by parameter prediction. In the future, we'd love to go from sort of high 60s to 90% accuracy on, say, CFAR. We'd like to improve the training speed of GHNs themselves from week to days, because we're interested in reducing compute associated with GHN training, not just the student network training. We'd like to move towards SGD-like behavior, generalizing to unseen tasks, not just unseen architectures, scaling up the models, increasing the granularity of the computational graphs. We'd like to improve our fine-tuning results. Like I mentioned in that sort of like toddler analogy, there's something that's going on that puts these networks in a region of the parameter space that stunts their further growth outside of the few shot scenario. And we should be able to understand better the loss landscape given our initialization. And we'd like to understand how and why these GHNs work, because they might actually help us to improve classical training with SGD. So with that, I thank you for your attention and give you some links to my group and CARE-AI at the University of Guelph. I'd be very happy to take questions.
Yeah, thank you very much. Very interesting talk. So now we have some time for Q&A. So I will start with a question. I mean, you kind of compare like the single pass approach with SGD performed for some iterations over some epochs, and you see, I mean, very good performance, but still there is, sometimes you showed like there is a gap in performance. And I wonder if you can think also of solutions kind of in between, like that you maybe are not completely one pass, but maybe allow for some kind of combinations, but be still more efficient than traditional SGD approaches.
That's really interesting to think about, and that's not the first time that question or suggestion has come up. I think that seems quite attractive, is sort of merging the benefits of parameter prediction and classical iterative optimization. Something which has been suggested before, which sounds very attractive to me, is the notion of kind of just-in-time network fitting. So just like at the time of making a prediction, you're going to do some adjustment by a graph hypernetwork, right, to a network that's been trained by SGD. That certainly we haven't investigated that. So I'm very interested. There's so many things we could do and haven't tried yet, but that's certainly on the list of intriguing experiments to run. Can we use graph hypernetworks to sort of reconfigure or update networks that have already been trained by SGD, or the other way around? Can we take parameter predicted models? And we saw some disappointing results where we tried to do further fine tuning with SGD, but it's early days, and I think we'll probably understand that better and be able to improve them at some point.
We have some questions from the audience. So how does your method work with customized models? And maybe if I would like to extend this question, I mean, could you also apply it, because I think you showed most results for image cases, but people in NLP domain or working with time series may have other requirements, other type of models. Could you also apply it to these domains? Have you applied it to these domains?
Great. So we have not, but there's no reason we shouldn't be able to do it. I think the reason we started in the image domain is that most of neural architecture search and related research has gone on in that field, we leveraged this search space of architectures called darts. That's what our computational graphs are built off of. And those were exclusively focused on the operators or operations that are found in the computational graphs of vision architectures. If one were to look at NLP architectures or other applications and create a search space like we did, it will take some effort to do that. But once you create that search space and define your operators, and if you put together, like we did, a set of architectures, like 1 million architectures that you could train the model on, our method is completely general in terms of the task-specific loss function you use and the data that you use as a task. So you should be able to do it for other domains. And I think NLP is an interesting one because it's been explored a lot in deep learning. There's many well-known architectures and good data sets for training. So it'd be natural to try that as well.
So we have another question on the impact of explainability of the models. Or maybe to also extend this one, you talked a lot about properties which you can also like predict, and I wonder, like, you could also think it further and try to predict or try to find models which are more explainable, which are more robust, which are better in some ways, which maybe are not linked to performance in the first place. Can you elaborate a bit on that?
I totally agree with that. I mean, I showed you this plot where we had explored 4 different properties, but the way that's done is we just extract an embedding from that graph hypernetwork, and we train a logistic regression model or linear regression model to predict parameters. And so, or predict properties, sorry. So we can add different criteria. For example, we might be interested in predicting robustness to adversarial attacks, or we might want to predict factors of explainability. Now, that will always depend on the difficulty of it automatically assessing these things, right? So something like explainability may take more effort to be able to collect those labels because it will involve humans, but there's no reason we shouldn't be able to do that. And I'm really excited about the opportunity to use those predictions of favorable properties to optimize the space of architectures. So we haven't done anything like we did NAS, but that is sort of using our process in an inner loop. You should be able to actually back propagate through this GHN into the space of the computational graph and start to do optimization in that space. And it'd be very interesting to be able to optimize that towards explainability or other properties. So that's sort of another future direction we'd like to go, but haven't really explored yet.
Mm-hmm. So another question is it something that could play a role in time-critical applications?
I believe so, because I had mentioned before this notion of being able to dynamically reconfigure a network with some newly observed information or a change to its task. If you're going to do that by SGD, that's going to take a long time. But by being able to predict in the space of parameters, I think this plays very nicely into time critical applications where you can have very task specific or even example specific adjustments. So I'm thinking things like mixtures of experts, which have a gating network that observes an example, and mixtures of experts choose how to weight a number of predictors to predict specifically for that example. You could do something similar to this, like you observe an example at test time and very quickly decide on how to change the parameters or combine parameters that are predicted through these graph hypernetworks and so forth. So I'm very excited by that. But again, it's not something that we started experimenting with yet, but certainly one of the more promising directions to move.
And I also wonder, is dimensionality an issue, or the number of parameters? Does it work better with models which have less parameters? Can you generalize better, or like what impact does the number of parameters have?
Yes, so that is one important detail, how we handled variable number of parameters, because we want to be able to predict for unseen architectures that, they just come in at test time and we generate the parameters, and architectures have different numbers of parameters. And we even saw these out of distribution examples where we want to predict a number of parameters that's much larger than the number of parameters that was ever observed at training time. So that's an important technical detail I didn't get into in this talk very much, but all the information is in the paper. And just to quickly sort of summarize what's happening is that we're doing some kind of parameter copying. Like we effectively generate some base parameters and then copy those out. So that helps us with being able to adjust certain, once a module grows much bigger, we have this kind of strided prediction. So I think that our procedure works. It can predict arbitrary numbers of parameters, but that aspect of it could be improved. And I think that at some point it's going to break down. Like I showed you how we could predict these out of distribution architectures, but if you give us something that's 100 million times bigger than anything that was seen at training time, I'm sure there will be at some point at which it breaks down. So yeah, I hope that answers the question.
Mm-hmm. Here is a question about the implementation of the GHN. It's in PyTorch, right?
Yes.
Could this reasonably be implemented in other frameworks?
Definitely. It's implemented now in PyTorch, but there's no reason why it couldn't work in JAX or TensorFlow or another framework. So, and I would love to see people grab our PyTorch code and port it to other languages. I would love to see more use. So if you're interested, we'd be very happy to see that happen and support it for sure.
We have time for one last question. So maybe I will have one in between. What about, I mean, I was thinking about because I'm also interested in federated learning, distributed settings. And I just wondered whether one could integrate this idea also to this context and this kind of applications, that you maybe not predict one or predict architectures or parameters, starting parameters in this distributing settings. Have you thought about that, or do you see an application which goes more in the distributing area of your approach?
Yes, I haven't thought a whole lot about that. What immediately comes to mind is that the approach to training that we do, which is sort of nested, we have these meta batches of architectures and meta batches of images, and we can parallelize over both. So that naturally is synergistic with parallel training. I also think that having a model outputting parameters and being able to drive the model towards certain criteria that we desire. So for example, criteria that are relevant to privacy may be another consideration, something else we could build into the GHN itself, make it aware that it's being applied in a distributed setting. But beyond that, I haven't really thought too much about how this could be used in sort of a privacy preserving manner or in a federated learning situation.
So we have one last question from the audience. Would this be something that would also work in encrypted space, for example, in fully homomorphic encryption?
Yeah, that's another, I mean, it's sort of along similar lines. And in terms of my response to that, I can't think of anything that would prevent it from being explored in that situation any more than SGD, but I haven't thought long and hard enough to say that, would this be more attractive to the homomorphic setting versus standard SGD. I think it's a really interesting sort of offshoot of this work. And yeah, if you're interested, I would be happy to chat more about it.
Great. So Graham, thank you very much for this exciting talk and a cool discussion. And yeah, I will now move to neural network and hope to meet you there, and take care.
Awesome. Thank you. And sorry, I guess maybe we can stop the recording. I have a couple questions, logistical questions. Is that okay, Reinhard, for the next part?
Yes, you go to the neural network, Ram.
How do I get onto the neural
Okay.
network?
I'll send you.
Oh, wonderful. Okay,
yeah.
perfect.
Okay.
See you there.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.